it by codimension 1 linear or affine subspaces, and you'll present this n-dimensional manifold as a family of n-1 dimensional manifolds that vary and undergo certain singularities. If you choose your slicing, the direction of your slicing generically, those singularities will be quite simple. And if I have some chalk, I'll just draw you a picture of a surface. Now you might slice it. And this is a standard way to produce a Morse function. Maybe many of you have seen. Well, let's take a very simple example. We take the two-sphere, and we simply slice it by horizontal planes. We'll get, well, nothing until this value where we get a point. That's a singular space. Then we get a family of increasing circles, decreasing circles. Surface, the torus. Again, let's slice it by horizontal planes vertically. This time we'll have 4 singularities. The initial one, the final one, and these 2 intermediate singularities, which reflects the fact that the sum of all the Betti numbers of this manifold is 4. There's a Betti number H0, rank 1, there's a Betti number H1 of rank 2, and a Betti number for the second homology, and that gives us a total of 4, whereas for the sphere we only have the homology in degree 0 and 2, and the 2 critical points. So there's a very close relationship between the critical points of these slicings and the homology and a whole calculus of how to compute the homology from these slicings. So this is what Frank Ray did for the 3 manifold, but he wasn't interested just in calculating the homology. He was interested in understanding a presentation in terms of simpler objects of the entire 3 manifold, and the picture that he produced goes under the name of the Heggard decomposition. It had been introduced by Heggard earlier. So if you take an appropriate slicing of the manifold and you look at sort of halfway through the process, you will find that what's below your slice is what's called a solid handle body. I've tried to indicate one of genus 2 there. So its surface is a standard surface picture I have here is of genus 2, but that's the level, that's this intermediate slice. But what's below the intermediate slice is the interior of that surface standardly embedded in free space. So that's a solid handle body. The one I pictured is of genus 2. That's clearly one of any genus you want. So that's what's below your critical level. What's above your critical level is the same. It's homeomorphic. It's another solid handle body. So you have 2 very concrete, compact 3-dimensional spaces with boundary, and your manifold is made by gluing those 2 together. And of course, the difficulty, the interest, all the complexity comes in how you glue those spaces together. So this is how Frank Ray wanted to study 3 manifolds. The whole problem reduces to questions of how you glue one solid handle body to another by a homeomorphism of the boundary. And this is what the Heggard had introduced, called the Heggard decomposition of the 3 manifold. Okay? Now, in fact, life is really simpler. We can concentrate all our activity on this surface. So if you want to describe a solid handle body, the first thing you have to do is give it the boundary. You have the surface of genus G, 2 in my picture, and then you have to say which circles on the boundary fill into disks in the interior of the solid handle body. Well, there'll be G of those circles. So a solid handle body can be described by giving the surface of genus G and then G particular curves all embedded in disjoint on the boundary, and I've written down a couple of properties that they have to have. You make the solid handle body by attaching disks to those circles and then filling in the rest with the 3 balls. So I've tried to indicate here the standard solid handle body as it's embedded in free space. There's the surface of genus 3. There are 3 curves on it. If you fill those curves in with disks and then fill the rest in with a 3 ball, you'll get the solid handle body, which is represented by the interior of that surface in free space. Of course, there are many choices for these curves, but that's how you can represent a solid handle body. You have a surface, and genus G, and on it a collection, a family of G embedded simple closed curves on the surface. Okay. But now we have 2 handle bodies. Our 3 manifold is described by one surface bounding 2 different handle bodies. So our surface is described by 2 families of curves, G curves, on this surface. And each one is equivalent, that is by a homeomorphism of the surface, to a standard family. But the problem is how they meet each other, how they're related to each other. So I just said that. So I've drawn you a picture to indicate, this is in fact a picture out of Frank Ray's article. This is the counterexample. So this is a handle body, or rather this is a picture of 2 handle bodies. So this is a picture of a 3-dimensional manifold. 3-dimensional manifolds are now pictured or represented by 2 families of curves. So here I have 2 red curves. Colors maybe don't show up so well here. The red curve here and the red curve here, which are completely standard. So they're describing the handle body that's the solid thing you see here. That's maybe the part of the manifold below the surface. Then I have the part of the manifold above the surface, which is a solid handle body with the same boundary. So it will be represented by 2 embedded closed curves on the surface. And here they are. There's this one that winds around this way, and then the other one in a slightly different color. Okay. Now you have to check that there is a homeomorphism of this surface to itself that carries those other 2 rather exotic-looking curves back to completely standard-looking curves. But indeed there is. It's not too hard to show. So this is a picture of a 3 manifold. What 3 manifold is it? How do you calculate its homology? How do you calculate its fundamental group? Well, Frank Ray knew how to do all of those, and he describes it. The way you calculate the homology is you take the determinant of a matrix. And the matrix is the matrix of intersection numbers of the red curves with these other exotic curves. So we have 2 red curves, C1 and C2, and we have 2 exotic curves, now labeled K1 and K2. Let's see how many times K1 meets C1. And this has to be a signed intersection. So I forget which way. I guess this is -1, +1, +1, +1, +1. So I have 4 + 1, 1 - 1. That intersection number is 3. Let's see how K1 meets C2. 1, 2, both are the same sign. +2. C1 meets K2. There's C1, K2 meets it twice, both in the same direction. -2, and the last intersection number turns out to be -1. So let's just go back to the matrix. You calculate its determinant. You see the determinant is +1. That means that the first homology of this 3 manifold that you're making by gluing together 2 solid handle bodies is trivial. If the determinant were 0, the first Betty number would either be 1 or 2. If the matrix is identically 0, the first Betty number is 2. The matrix is not identically 0, but its determinant is 0. The first Betty number is 1. If the determinant is non-zero, the first Betty number is 0, and the torsion coefficient, the order of the torsion group, is the absolute value of the determinant. So this manifold has trivial homology because the determinant of this matrix is 1. What about its fundamental group?